Hey everybody, it's Miss Pasega, and today I'm answering the question, what the heck is a quadrupole and why they're useful? So I thought it was kind of unfair that I gave you guys this big project to do if I'm not willing to do it myself. So I decided that I would make one for myself. My experimental question is, what the heck is a quadrupole and why are they useful anyways? So what a quadrupole is, as you can see, is a distribution of four charges, two positive and two negative. That makes the electric field at the center zero, so the electric force at the center is zero. And as a result, the quadrupole can be used to trap charges. A dipole, if you can imagine, a dipole would be two poles, and those naturally occur in nature all the time, like, for instance, the magnetic field of the Earth, a dipole. The electric dipole moment of water. It has a positive side and a negative side, i.e. a dipole. And we know that a pith ball can become polarized when put near a positively or negatively charged ion. So, what we're going to be doing is we'll be working with a gravitational, magnetic, and electric quadrupole. The picture on the left is a gravitational quadrupole. It has two peaks right there that represent positive potentials, and the two troughs down at the bottom, those represent negative potentials. See how in the center the net force would be zero, except it's called a saddle point. The net force is zero, but it's not really stable. So check this out. Saddle points do have zero net force. In theory, you could make it be having equilibrium. But it's just not tenable because it's unstable on either side. Maybe you can get it to balance for a second, but it won't stay. You can make a saddle point stable in one of two ways. You can trap an object by rapidly rotating your potential. In this case, it's a gravitational potential, the shape of a quadrupole, of course. You could also do this by rapidly oscillating. In this case, our peaks and troughs are interchanging their positions rapidly. And if you are thinking of this in terms of standing waves, that's probably a pretty good idea thinking of it, because this would look like a node and antinode. Womp womp, another famous trap. Well, this creates with electricity what's known as a Paul trap. It's an electric quadrupole that rapidly oscillates to trap ions. Because there's no electric force on neutral particles, it won't trap them. So, here's an example of a Paul trap. It's holding ionized pollen that's vibrating up and down. Since it's changing its sign, we can actually see the frequency of the sine wave as it's changing because it has one particle that's moving up and down. The rest are kind of just vibrating in place. This experimental Paul trap looks much cooler, but that's because it's flour, so still a Paul trap, but it's being excited with a laser. Notice that the Paul trap is actually such high voltage in this case that it's arcing. Those little sparks going across are arcing from negative to positive. The electrons have so much potential energy that they can break through the dielectric of air. So here's what I did with my lab. I took a conductive piece of paper with an electrode overlaid. I didn't get a chance to take a picture of mine, so here's what it looks like with me drawing in two red positive electrodes and two blue negative electrodes. Fun fact, I actually did this as positive and ground, so my blues are not precisely negative, they're actually zero, which means when I do my configuration, it's going to be slightly different than in theory, but that's okay. My electric field vectors show that it's weakest at the center. We can see that all the other arrows are nice and bright, indicating strong electric field, but the center one has almost no field. It's strongest near the poles. Connecting those field vectors leads to field lines. So in theory, field lines point from positive to negative. The lines do not cross each other. And the denser the lines are, the stronger the electric field. Notice that there's no field density in the center of a quadrupole. So there's net force is 0. And this is the beauty that we've been waiting for. So I made an electric potential map just like you guys did, except I decided to be super precise in mine, and I actually did every point. So you guys had skipped and had done about half. I did every point, including all the odd points, to make this equipotential map. You can see the 2 positive peaks corresponding to positive potential, and the 2, I'm not going to call them negatives, because remember I said that I connected my blue electrodes to 0, so I can't get a negative potential difference here. They are going beneath the average of 5, and think of it as, in this case, the equilibrium is 5. My zeros are less than that, so they are getting a negative potential difference. They're just not giving me a negative potential. Thing to notice on this last go around is notice that the center, the saddle, has the same blue everywhere. No, not in that screen. There we go. It has the same cyan blue color everywhere in the saddle point, meaning the net force is 0 because the electric field is constant. Here's my equipotential maps. See how I have 0 potential in the center? That's what those 2 lines are, closest to the center of the trap. I have negative potentials near my negative poles, positive potentials near my positive poles. So, in conclusion, a quadrupole potential would be 2 positives and 2 negative charges. They trap particles because the net field is 0 in the center, and therefore the net force is 0 in the center. The potential at the center is constant, and so a saddle point is created. As the field trap changes rapidly, it oscillates back and forth, trapping the particles where they are. Finally, you can't see all of this on the screen, but the applications include levitation, which you saw. But moreover, my master's work was on the separation of ions from atoms in gases. Otherwise, how else would you separate them? The atoms would pass right through the trap. The ions would get stuck in the center. Then when they get excited by a laser, they look like little tiny suns. So, thanks for watching. I will post the PowerPoint of this online so that you guys can see the actual correct citations as well as the edges of the presentation. So notice that all the figure citations got cut off by the edge of the presentation here. Check it out later so that you can see the bibliography slide to make sure yours is done in AIP format correctly. Thanks for watching.